In this video, we will be looking at section 4.5, which covers graphs of logarithmic functions. So we're going to start by talking about some graphical features of the logarithm. So in general, if we are looking at the function g of x equals log base b of x, then graphically there will be a horizontal intercept at 1, 0. So here you can see three different logarithms. We have log of x, ln of x, and log base 2 of x. They all pass through the horizontal intercept 1, 0. The graph has a vertical asymptote at x equals 0. So you can see that these all go towards negative infinity as they get closer and closer to x equals 0. The graph is increasing and concave down. So as they're coming up from negative infinity, they're going up and to the right. The domain of the function is x is greater than 0 or 0 to infinity, meaning that the argument, this thing inside the parentheses, has to be positive. And then the range of the function is going to be all real numbers, so you can get any y value out of this function. So the range is negative infinity to positive infinity. So we're going to see if we can find the domain of some of these functions. First up, we have f of x is equal to log of x plus 2. The only thing I care about is the argument, this thing inside the parentheses. So in this case, x plus 2. It has to be positive, meaning greater than 0. If I subtract the 2 over, we get x is greater than negative 2, which we write in interval notation as negative 2 to infinity. And that's all there is to it. In the next one, we're looking at the natural log of 5 minus x. Just like last time, I don't care about anything other than the argument. In this case, that is 5 minus x, and I need it to be greater than 0. If I add the x over, we get 5 is greater than x. But it's kind of hard to read it this way. It's easier to read if the x is on the left. This is saying 5 is bigger than x. So if I flip it, that means x is smaller than 5. So x is less than 5. So our domain would be negative infinity to positive 5. For the third one, we have 2 log of negative x plus 1. Again, we only care about the argument in here. Negative x has to be greater than 0. To get the x by itself, I need to divide by negative 1 on both sides, but I am dividing by a negative. If you divide by a negative, or multiply, then you have to flip the inequality sign. Right now, it's a greater than, so I'm going to have to flip it to be a less than. And we get x is less than 0. To write x is less than 0 in interval notation, that's going to be negative infinity up to 0. Now, something that we saw with exponentials was how similar they could kind of all be, but logs are even stranger. So if we think about the change of base formula, then log base b of x can be written as log base c of x over log base c of b, which is the same thing as 1 over log base c of b times log base c of x. And I know that looks really strange written out so generically, but what that means is log base b of x is a vertical stretch or compression of the graph of the log base c of x function. So this is equal to this, and this number out front is just that. It's a number, so it's a vertical stretch or compression. So this tells us that a vertical stretch or compression is equal to a change of base. So for this reason, we typically represent all graphs of logarithmic functions in terms of the common or natural log functions, and then we just vertically stretch or compress them from there. So if we think about what a horizontal compression would do, consider f of x equals log of cx. By the sum of logs property, we could write this as the log of c plus the log of x. But this log of c is just a constant. So the effect of a horizontal compression is the same as a vertical shift. This graph is just a shift vertically of log of c. So we're going to be able to write every single logarithmic graph in terms of log or natural log, which is kind of cool. We're going to focus on using common log because that's what students tend to be a little more familiar with and a little more comfortable with. So any transformed logarithmic function can be written in the form f of x equals a log of x minus b plus k, or f of x equals a log of negative x minus b plus k if horizontally reflected. So we have to think about what that means. Our normal logarithm function is increasing concave down. If we horizontally reflect that, that would be flipping it this way. It would look like that. So the way I think of it is if the vertical asymptote is on the left, we're normal. If the vertical asymptote is on the right, we're going to have to do this little negative flip here. So let's see what that looks like. We're going to write a formula for the transformed logarithms graph. I'm going to bring in a separate sheet of paper so that we can look nice and close at these. So here's our first graph. Well, it doesn't look like our normal logarithm graph, but the vertical asymptote is still on the left. When it's on the left, then we get to use the standard y equals a log of x minus b plus k. B is our vertical asymptote. So what vertical line are we getting really, really close to? -3. So I'm going to replace b with a -3. That'll give us y equals a times the log of x minus a -3 turns into +3 plus k. Now I'm going to use other points on the graph to help me figure out what a and k are. I'm going to start by using my horizontal intercept, which is at -2, 0. So I'm going to plug that in to what I have. That'll give us 0 is equal to a times the log of -2 plus 3 plus k. -2 plus 3 is 1. So 0 equals a times the log of 1 plus k. But let's take a look at the log of 1. The log of 1 is equal to 0. So what this says is 0 is equal to a times 0 plus k. A times 0 is just 0. We're getting k equals 0. If k equals 0, then I can go back to this equation and plug in 0 for k. And we're looking at y equals a times the log of x plus 3. Now I need another point on my graph. It looks like we passed through 3, -3. So let's plug that one in. We'll get -3 is equal to a times the log of 3 plus 3. Believe it or not, 3 plus 3 is 6. So we get -3 equals a times the log of 6. So a is equal to -3 divided by the log of 6. Plugging that into our equation, we get that this is the graph of y equals -3 over the log of 6 times the log of x plus 3. That's what we're looking at. Now remember in the beginning when we were first looking at this graph, I said, well, it doesn't look like a regular logarithm graph because it's not increasing. Well, we said that the vertical asymptote is still on the left. We had a -a value. It was a vertical reflection. We only do the weird negative thing with the equation if it's a horizontal reflection, and we didn't have that. This one was a vertical reflection, and it fell out when we were solving for a. So let's try the next one. Does it look like a regular old logarithm graph? No. Is the vertical asymptote on the left? No. So this is one of those that is horizontally reflected. And if it is horizontally reflected, then we need to use the equation y equals a times the log of negative x minus b plus k. So what makes it special is when there's a horizontal reflection, we need a negative in front of our x minus b. So our b is our vertical asymptote, which happens at x equals 3. So I'm going to plug that in. We have y equals a times the log of negative x minus 3 plus k. I need 2 points on my graph to help me solve for a and k. I try to start with my horizontal intercept because that gives me a value of 0 in here somewhere that helps out, because that's at 2, 0. That gives me a 0 for y. We get a times the log of negative 2 minus 3 plus k. So 0 is equal to a times the log of negative 2 minus 3 is negative 1 plus k. So 0 equals a times the log of positive 1 plus k. But we saw that the log of 1 is 0. A times 0 is 0. That's gone. We get that k is 0. That looks familiar. If k equals 0, we can plug that in, and we get y equals a times the log of negative x minus b. Oops, we said that b is 3. And then we don't have our plus k at the end anymore because it was 0. So I need another point on this graph. It looks like it goes through negative 2, negative 4. So let's plug that in. So negative 4 is equal to a times the log of negative 2 minus 3. So negative 4 equals a times the log of negative 2 minus 3 is negative 5. And a negative 5 turns into positive 5. So that means a is equal to negative 4 over the log of 5. So that means our equation is y equals negative 4 over the log of 5 times our log of negative x minus 3. So the negative in front of the x minus 3 indicates that we had a horizontal reflection of this guy. And the fact that our a value is negative indicates that there is also a vertical reflection. Let's try this third graph here. Does that look like a normal logarithm graph? It sure does. So we get to use the regular formula. Y equals a times the log of x minus b plus k. I'm going to start by plugging in my horizontal intercept at negative 3, 0. Oh, sorry. We know that our vertical asymptote is at negative 4. Let's plug that in first. So y equals a times the log of x minus a negative 4. So that turns into x plus 4 plus k. Now I can plug in my horizontal asymptote, or sorry, horizontal intercept. We get 0 is equal to a times the log of negative 3 plus 4 plus k. But negative 3 plus 4 is 1. So 0 equals a times the log of 1 plus k. The log of 1 is 0, so that's gone. K equals 0. You might be catching on to something, at least for this class. So if I plug in k equals 0, then we have y equals a times the log of x plus 4 plus k. So I need one more point on my graph, and it looks like we're going through negative 1, 2. So if I plug that in, we get 2 equals a times the log of negative 1 plus 4 plus k. So 2 is equal to a times the log of 3. Oops, I don't need this plus k. K is 0. Dividing both sides by the log of 3, we get a is equal to 2 over the log of 3. We have a positive a value this time, so there was not a vertical reflection. So now that I know what a is, I plug it in, and we get y equals 2 over the log of 3 times the log of x plus 4. That is what we have graphed.